Report today for you? Well, we've got some news from the Mars Center. This is the Miller Advanced Research and Solutions Center, which is a part of Weber University and is located actually at Hill Air Force Base. And then you, of course, know now that the Mars is a very appropriate name for this high-tech university research center. Now, they have recently purchased an Impossible Objects composites-based additive manufacturing system, or CBAM-2. So it's a very capable kind of matting-based or 3D printing technology that allows you to make composite structures that are very complex and really useful for aerospace structures. Like things like cabin doors or structures of maybe even potentially at one point seats for aircraft that could be thinner and actually at the same time more comfortable, that kind of thing. And so it makes a lot of sense for the Mars Center, especially since it's located at Hill Air Force Base, which is a really significant Air Force base for the United States Air Force. They could do a lot of really cool things with it. Now, one thing that caught my attention that they're doing with it, I think, is it's really groundbreaking, and it has been going on a little bit, but I'm very, very excited about it, is what they're doing is they're upgrading existing spare parts. And I think this could bring a huge market to 3D printing. The automotive aftermarket, just all the spare parts and things, and sometimes they're straight up spare parts, but sometimes aftermarket parts are kind of additions or kind of things that are meant to make your car look even cooler or in some cases much uglier. And this is a huge business. This is like a $600 billion business. But imagine if we had an aftermarket for all the things in your house. That is, of course, a huge market as well. But imagine if we didn't only do straight up replacements, but we did refinements of everything. So imagine at one point if you had an air conditioner and the panel on it broke. And instead of just getting a straight up replacement, which of course would be cheaper to make with another technology, we would make a 3D printed air conditioner screen that would improve your airflow, for example. And then you could, at lower energy usage, have the same coolness effect on your room. Now imagine what that would do, just to show global energy consumption, but also imagine what kind of a market that is. You're not offering somebody like a $5 replacement spare, you're going to offer them a $20 kind of improvement to your existing air conditioner. So what if we started looking at everything in the world, not as disposable, but more as a kind of a huge installed base that could be an aftermarket? Now, one surprising area where we're seeing this is, well, these improvements to spare parts is by these Mars guys using the CBAM system. So what they did is they're looking for a part on legacy aircraft. These are aircraft that were made in the 70s and 80s, and they have straps for first aid kits. Now, these straps for first aid kits were made for a previous generation of first aid kits 40 years ago. Now, of course, they're of course subject to kind of strain and being used all this time. At the same time, the Air Force in the interim has expanded its first aid kits. The first aid kits now are much heavier. So what happens? Well, these straps are breaking. They can't replace them with the legacy technology. The technology is lost because it's been a couple of decades or it's too expensive. So what they did is they used CF PEEK or carbon fiber PEEK and the CBAM system on Impossible Objects to print these spare parts. And now they're new and improved spare parts. They're not a straight up one-on-one replacement. No, they're meant to do with cope with the new packs. So imagine the potential of doing this and this kind of improvised engineering, and imagine the potential just in the military sector of rolling out slightly improved controls or slightly improved ergonomics. And just imagine what that would do to improve the military. And imagine in a broader sense what that could do for society as a whole. So I think that's, this is a really very, very exciting development, and that's why I wanted to kind of put some attention to it. The next thing is by the University of Colorado, and that is a paper called Defining Soft Tissue Bitmap Printing of Soft Tissue for Surgical Planning. This is by Robert MacCurdy and a lot of other people, the CU Boulder and CU Anschutz Medical Campus. Now, what these guys have done is they have taken regular CT and MRI scans, DICOM files, and made a better representation of the body, essentially. What they say is, think of existing methods of representing an entire orange by only considering the exterior orange peel. That's a quote from MacCurdy. When viewed that way, the entire orange is peeled. And what they're now doing is they're kind of defining the insides of the soft tissue of the body, and they've tried this with a kidney and a heart and some other organs, and as voxels. And this voxel level definition they've written software that takes the DICOM files, which is the standard imaging format for medical, and turns these into these bitmap files, which are defined on a voxel level, and then you can give voxel level properties to this organ. So you can get a soft tissue that is much more representative of what the soft tissue is actually like. And then you can get different levels of hardness, or different levels of strain, or different materials, maybe even different colors, anything you want. So this is a much, much better representation than doctors are useful. Now, I know what you're thinking. This is really great news for Stratasys. Of course it is, because Stratasys, they've done a 6-material bitmap file, and this could be great, of course, for the Stratasys J750 and these other material printers, the Object type systems that they have, that are specifically meant to improve soft tissue modeling and give better soft tissue. This could be great, but it could be great for other people who are trying to get into this medical modeling kind of area. And generally, this kind of representing everything in a much more voxel level way could be much, much better for industry. And that got me thinking too about backpacks. So we can now buy the Jack Wolfskin Aerorise backpacks online. Now these backpacks have 3D printed panels on them, 4 of them. They're 3D printed by Oechsler on a carbon system, and this system, the material is EPU 41. It's a dual cure energy return elastomer. And what they've done is engineered these things. We've talked about them before, just in case you missed that. We've engineered these things so that they have a lattice structure, and that lattice structure improves the breathability of this back and reduces the temperature on your back, so it's less hot and less sweaty, and gives you better ventilation even when the back is compressed. And it kind of lightens the load by redistributing it in an intelligent way. And so this is 4 independent parts. You can see them on the backpack on the left. Now, Carbon at the same time has invested in Parameter software to expand its kind of capabilities in software, and has developed its own lattice planning software as well. But what if, right, we look at this thing in a more individual way? Now, at the moment, if you see these panels in front of you, it's kind of, they have different properties depending on where on the panel you are. So if it's closer to the back, the mesh is actually firmer, right, to make it more stable. If it's closer to the skin, the mesh is actually softer. If it's closer to the back part and the middle and in the bottom, there's actually a softer zone as well, right? But to help you carry the weight. So across these it's a uniform looking part, but across the part they can assign different properties and give different strengths to these lattices to it. What if we made this individual? What if we combined the carbon software and the carbon 3D printing with something like Trinkle or Twicket, and then we developed a thing that, according to your preferences, according to the loads you carry, and according to your individual back and your musculature and stuff, you would get an individual back pad. Not only like one sized for you, but one that has the qualities that you are looking for, the type of support that you are looking for, and is changed across this gradient, across this material, at a voxel level for your specification. Now, to me, this has always been the dream. Like, I don't understand 3D printed insoles that are just like a particular shape, but I would understand them if that shape is unique to me, and also all of the properties at a voxel level are unique to me as well. So at exactly every different point, the thing is unique. And to me, then, we look at carbon and other technologies, then you can really have individualized tennis rackets, or think of headrests, and all these kind of things that don't only conform to the shape, but the actual needs you have, and the desires you have, and the type of comfort you want. So I think that could be super duper exciting. Anyway, that's what I wanted to bring to you today, and I hope you enjoyed this edition of the 3D Printing Unpeeled. My name is Joris Peels, and this is all thanks to 3dprint.com.